EC 111 lecture 14, set 2. We continue with describing what the final project is and, what are the description of the final, list of explicit things that you are going to do for the Bitcoin hashing. So as a reminder, Bitcoin's header has a few fields that are typically constant. And for the purposes of this project, we have one field, which is the version of the block version number. And every time you upgrade the software, it specifies a new version, and this is important in practice. And then there is the field for 256-bit hash of the previous block header, and it's updated when we have a new block, and the size of this is 8 words. The hash Merkle root, which is the hash based on all the transactions in the block. And that one is also another 8 words. And every time you accept a transaction, we're going to add it to the block of the previous kind of Merkle transactions. Time is important because, as we have seen before, there are a lot of entities that are trying to verify each of these blocks, and every time one of them is verified, we need to get a timestamp to realize who has done this computing first, because they're the people who get the Bitcoin. And then this one is going to be upgraded every few seconds. The next field is the bits. Which is basically the difficulty of finding a hash. So based on the threshold of which number you want to set and which number you want to find that your hash value is smaller than, then there is more difficulty, because if you have say you put the difficulty at 10%, so 90% of the hash values are larger, 10% is smaller, then every 1 out of 10, you will have a chance of finding the hash that satisfies your constraint. Now, if you put it to be 1,000th of the range, then you need to try 1,000 random numbers to get to that, in average. If you put it to be 1 to the power, 10 to the power minus 20, then there is 1 in 10 to the power 20 chances that after so many iterations you will find it, which is basically becomes like a really huge number. This will be like 2 to the power 60 almost, and that is kind of not really what what is practical. But as time goes by, they adjust this threshold, so because there are more entities that are trying to compute these hash values and try to mine, so they try to make mining more and more difficult by setting this threshold. And then there is a number used once, or a nonce, which is what the variable is that the people who are trying to compute have the degree of freedom in changing. So they're going to change this nonce, and every time they change the nonce, they're going to compute the value of the hash and then add it to the transactions, and then basically every time you get it, then we are gonna increment this by 1. Now the input message now. So if we look here, there are 19 words for the first 19, the first 1, 2, 3, 4, 5 items, and the last one, which is basically being changed, is 1 block. This makes 1 plus 1 plus 1 is 3, plus 16 is 19, and with 1 word for the nonce, this will make 20 words. Now the input message is of the size 20 word, where 1 word is 32 bits. Then the total input message size is 20 times 32, which means it's 640 bits. Now, if we are talking about the Bitcoin, the size of, it's a standard block size we have for the Bitcoin, which is 512 bits. So as you see here, we have 512 bits, and then 128 bits is added to that. So we cannot have one digital block. We have to have two digital blocks pre-created for each of the input messages. And this is stored in memory, which is instantiated in the test bench code. So when you're writing your code, we have the test bench. So the actual bit message is, you know, something we're going to read from the test bench. And the actual content of this input message is not important, you know, in code development and simulation to us, because, you know, it's when we're running this in real life, it could have any of the numbers that, you know, is possible. And as you see here, every time, you know, we have one of these, the first 19 words are stored in memory, and these are metadata. These are not like the data that we are going to change. The only thing that we are going to change is this last word, which is the nonce. And, you know, this is one final word that it has. So, and then remember, what we're going to do is we're going to use a SHA-256 to create output hash value for each digital block. So there are two digital blocks. There will be two hash values created, which means that we will have one hash value for each block. Now, for the sake of simplicity and convergence, we only assume 16 nonce value. So, you know, in general, if we have a 32-bit nonce, that means we're able to generate 2 to the power 32 different numbers, but we're not going to consider this range because it's going to be like just a lot of computation, and you know, we don't have as much resources. In particular, if we want to do some parallelization, we're going to limit, for the sake of the simplicity and practicality, this project to 16 nonce values from 0 to 15. And so every time we want to try different hashes, that means that we will have 16 attempts to create a hash value for each of the blocks that we are considering. And you know, another thing to consider is that because those 19 words are fixed for each of the hash values and only the 20th was added, the first 16 words, which is 512 bits, are the same for all the calculations that we are going to have. And for the second block, the hash value is created 16 times. And, you know, every time we do this, we increment the nonce by 1. So this is the, you know, this is a block diagram for this. And, you know, what happens is that we are going to keep trying new nonces until the final hash is smaller than the target goal. Again, for the purpose of the practicality, we don't really look at the actual hash value in this project. We're just going to compute exhaustively all the 16 choices, and you know, there's no comparison at the end to any kind of threshold. And you know, we considered, once you compute these 16 values, then you know, we consider this as a complete. So you know, now remember that we have 512 bits, and then we have 640 bit messages, out of which the first 512 are the same, and then the last 128 bits are different. And now for these blocks that are in the second block that are different, we also have a number of don't cares. We have basically 512 minus 128 bits don't care. And in order to make sure that, you know, we kind of get this, you know, right, and that's actually what happens in reality in Bitcoin, is also they pad these messages, and that the instruction for the padding is given, you know, in the project. And you know, once we have the you know, 256-bit message, it is kind of the same. Because the input is you know, 512, we need to pad it to, again, back to the 512 bits to get the you know, to get the block value. So the key observation here is that for the first block of the first hash, the hash computation is the same for all nonce values. Therefore, we don't need to compute this multiple times. We can only compute this once. Based on this, we are going to divide this computation into 3 phases. The first phase is that we are going to take the first block of the first SHA-256 hash function, and then what happens is that we are going to take this constant as the initial values of the hash, and then the first 16 words in the memory that are the metadata that are consistent across all hashes, they're going to use as the input to this SHA function. Again, this SHA function is going to be used once because that value for the first 16 bits is going to be constant. So that is easy. We take care of that. And remember, this is, a hashing, so we need to chain this. So for the rest of the block, because we are considering 640 as one block, for the rest of the block, we're going to use the hash of the first block, which is constant. For each of the nonces that we add, the processing of the second block is, we get the results from the first SHA-256 function, and therefore this initial values come from the output of the phase 1. And then the words that we are going to read from the memory is going to be, the nonces, the padding, which you will see here. Kind of the 0 zeros are kind of padding this, and then kind of this value. Okay, now, in the phase 3, we have a second SHA-256 hash function, and the second SHA-256 hash function has its input, which corresponds to, to the constants again. So the initial values for this are the constant. And then the input to this is the output of the phase 2, in addition to the padding, as you will see here, and the kind of initial header of the file, which talks about the sizes. So the phase 2 and phase 3, because they're reliant on the nonce value, are performed 16 times. And so this will produce 16 final hashes for us. Now this will compute the final hash, which is the SHA-256 nested with SHA-256 of the message for 16 nonces, for each of the message, which has a block header and a nonce, and then we get this 16 values, H0 in position 0, H0 in H1, H2, all the way to H7, which are the output of the hash, and we get these output, like these 8 words output for the 16 nonces that we have. So we will just write to we could do this writing to the memory every time to a new location, but for the purposes of this project, we will just write to memory location H00 to H015 a total of 16 times. So the assumption is that every time you write it, then we could kind of store it, and then you kind of go further for the purposes of this project, because we don't want to use like all the possible registers and resources there. Next subset, I'll be talking about hints and optimizations for this.